Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about B-type and U-type instructions in our RISC-V, where we have previously covered about R-type instructions and we have also covered about I-type instructions and S-type instructions. Now, in this particular session, we are going to cover about B-type instructions and U-type instructions. Now, coming to my B-type instructions, basically this B-type instructions stands for branch instructions, and this are use it for branch operations, and B-type instructions encodes conditional branches, and we are going to have a 12-bit immediate which is going to represent a signed program counter relative byte offset, and it is always a multiple of 2. So bit 0 and bit 0 is never stored. Okay, so this is nothing but my B type format. And first of all, let us see the encoding format of this particular B type, where I'm going to have immediate of 12 and immediate of 10 down to 5, and immediate field is split between immediate of 12, and next is immediate of 10 down to 5, and next is rs2 source register 2 source register 1, and function 3 for deciding what kind of branch operation it is, and next is immediate 4 down to 1, and next is immediate 11 are also split like this, and next is opcode. Opcode is basically, we already know that kind of instruction, what kind of instruction it is for finding. Now, that is what this particular fields are representing. Now, why is immediate bit scramble? So basically, RISC-V is going to use the same bit positions across S type and B type. So immediate generation hardware can share wiring. So that's the reason here immediate bit is scrambled. We are going to uh, basically we are going to concatenate it from immediate 12 down to 1, which is nothing but immediate of 31, and immediate of 7, and immediate 30 down to 25, and immediate of 11 down to 8, and last bit should always be equal to 0. Okay, and bit 0 of the immediate is always 0 because branch targets are always 2 byte aligned, and in our immediate of 31 is a sign bit, and it should be extended for filling the remaining bits. So this immediate value is a 12 bit immediate value, right? So we need to sign extend it. This we have already seen in our previous instructions also, when we were discussing about I type instructions, and in S type instructions also, whenever we were having this 12 bit immediate value, we were basically sign extending it to a 32-bit value. All the remaining bits of the MSB will be filled with our sign bit, and the range of this particular is plus or minus 4 kilobyte from the current program counter. Okay, so this is and my target address is computed as program counter plus immediate value. Okay, now let us see how exactly we are going to perform the operation and all. So here you can see we have a particular assembly language code written BEQ, which is nothing but branch equal to. Now, what are we going to do? We are going to compare the contents within X5 register and X6 register. Now, if these two are equal, then label is basically 8 byte. Now, what are we going to do? If these two are equal, then we are going to increment our program counter by PC plus label, which is nothing but PC is equal to PC plus 8 bytes. This is what we are going to do in the case of our branch equal to instruction, or whatever the branch instructions. And this particular label is nothing but the immediate value which we are going to provide it in the instruction itself. Okay. Now, this immediate value, whatever we are providing, it's a 12-bit value and will be sign extended to 32-bit value. And since it's a 12-bit value, the maximum range which we can go is 4 kilobyte plus or minus 4 kilobyte. Forward we can go to 4094 bytes, and backward we can go to minus 4096 bytes. So that is what we have written here over here. So the range is plus or minus 4 kilobytes from the current program counter, 2's complement, and 13-bit effective value. So the target address is computed as PC plus immediate of not of RS1 plus immediate. Okay, so it is computed as PC plus immediate. It's not RS1 plus immediate. So we have basically 6 kind of branch instructions. One is branch equal to. That means when we are going to compare RS1 and RS2, if these are equal, then we are going to have the jumping, or incrementing or decrementing of our program counter according to the logic which we are going to have. Let's say suppose if the immediate value is a negative value, then we are going to perform PC is equal to PC minus the immediate value. That is what we are going to do. And next is branch not equal. That means if the two register contents are not equal, then we are going to set whatever PC is equal to PC plus the immediate value, or it might be PC is equal to PC minus the immediate value. Next is branch if less than. So if RS1 is less than RS2, and here the we are going to have the signed RS2. RS2 is a signed value. And next is branch greater than. That means we are going to compare RS1 is greater than or equal to RS2, and here also RS2 is signed. And branch less than unsigned, where RS1 is less than RS2 and here RS2 is unsigned, and branch greater than unsigned. So these are the different kind of branch instructions which we are going to have, and these are decided by the function tree. Now, let's see one more example where we have written this particular C source, that C code, where it has been converted into RISC-V assembly. And here we are going to have the branch checking. So if this particular condition is met, we are going to have this particular done condition. So this is how we are going to write down our particular, and this is where we are going to use our branch instructions. Like let's say suppose if I'm going to have a particular instruction which is written, I'm going to decode it, and I'm going to split it across this particular fields, and I'm going to my particular decoder is going to decode it, and it is going to decide what kind of instruction it is, and it is going to execute that particular kind of instruction. This is about our B type instructions, where we have discussed about what is my branch instruction and how I'm going to calculate the target address and what is the immediate range I'm going to have, and the field order and the 6 variants which we have discussed. Next, we have something known as U-type instructions. So U-type is the simplest RISC-V format, and it is going to have a 20-bit immediate, and it is going to occupy the top of the instruction, place it directly into the bits 31 down to 12, and 31 down to 12 of the result, and no reordering is needed. So here immediate value is placed on the top of our instruction, and it's a 20-bit value placed directly into the upper 20 bits of 32-bit result, and the lower 12 bits are filled with zeros. Okay, so like let's say suppose if I want to have a particular load upper immediate instruction, if I'm going to write down RD is equal to this one, LUI X5, and this is a 20-bit instruction. So I'm going to write down LUI X5 is my destination register in this particular case, and I'm going to write down my 20-bit value. Okay, now what is going to happen here? X5 is a 32-bit register. X5 is a 32-bit register, and upper bits will be filled by the 20-bit value. So all the 20-bit value will be filled with the upper bits of your X5 register, and the lower remaining bits, that is my 12 bits, will be filled with zeros. This is the difference between load upper immediate instructions and the remaining instructions. Whereas in the remaining instructions, we were loading the registers lower bits with the immediate value, and the upper bits were sign extended. If you have remembered in I type instructions and in S type instructions and B type instructions, where the immediate value was sign extended, and if you want to load it, you are going to load them into the lower bits of your register. But in the case of your load upper immediate instructions, you are going to load the 20-bit value into the upper bits of your register, and the lower bits will be made to zeros, and you're not going to perform any kind of sign extension over here. This is nothing but my load upper immediate instruction, and this is U type instruction. So in U type format, I'm going to have two kind of instructions. One is load upper immediate, and um, add upper immediate to the program counter. So this is what I'm going to have. So where RD is the destination register that is going to receive the results. Okay, and this is opcode, which is going to decide what kind of U type instruction it is. And here we are not going to have any kind of scrambling of our immediate value. So you can see over here, this is what I was saying about. So I'm going to place a 20-bit value into the upper 20 bits of RD, and zeros the lower 12 bits, used to construct large constants or upper half of a 32-bit address. Okay, and coming to AUIPC, add upper immediate to the PC, where I'm going to add program counter with the 32-bit value immediate value. Okay, so what is this? Basically adds a 20-bit value shifted left towards 12 bits, and to the current PC, and it is going to enable PC relative addressing far behind the plus or minus 4 kilobyte range, because previously when we were using this particular immediate value, the maximum range which we can add our program counter was only plus or minus 4094 to minus 40 plus 4094 to minus 4096, because our immediate value was only 12 bit. But here in the case of my AUIPC, I can have the immediate value which is basically 20 bits, right? And that's the reason I can basically go beyond the range of plus or minus 4 kilobyte. And what is the instruction it is going to look like? This is how it is going to look like: AUIPC x6 and 2. This is my 20-bit immediate value. And what is going to happen? X6 is my destination register. So I'm going to basically add this immediate value with my program counter. So program counter plus this particular 20-bit value, and this 20-bit value is also left shifted to upper bits, and it is basically a 32-bit value, where last 20 where the 20-bit value is left shifted and remaining bits will be zeros, and we are going to add this particular entire content to our program. Okay, and the resultant will be stored inside your x6. Okay, this is how we are going to perform AUIPC. Yes. So that is about my LUI and AUIPC and B type instructions and U type instructions. So this is about our all the instructions, and we are left with one more instruction, and after this we are going to start developing all the particular modules in Verilog, and we are going to verify them. Yes. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.